Good evening viewers, welcome to this session of teleconferencing. Today's topic is mathematics for economic analysis. This pertains to the BDP program's course number EEC5, which is shortly to be presented to you as BECE 15 in its revised form, and this is a course that deals with elementary mathematical methods in economic analysis, and this is what we discuss today. We shall discuss both about the content as well as something about the structure of the new course which is to be offered to you. Now, let us begin straight away and say why mathematics is needed for economic analysis, or what is the advantage that mathematics provides over a straight and simple verbal analysis. After all, most social sciences or many topics or many subjects are explained or taught or discussed using only verbal methods, or at best some diagrams. Why then should we use mathematics? You might feel that mathematics is appropriate only for the sciences. Subjects like physics or chemistry, one would think, is what mathematics is needed for. And indeed, in school and other places, when you think of economics, you think of it as a social science, as an arts subject, and you feel that mathematics is probably not needed. But that is not a correct view. Now, if you look, you'll see that mathematics provides certain advantages, and that is the language of mathematics makes for precision. When we speak in a normal verbal form, we sometimes present arguments which are not very precise. You can see by your everyday use of language, you talk to your friends, you discuss many things. When you say, after you have said it, then you feel that, well, it could have been put in some other way, it could have been explained in other way. But in mathematics, that is not quite the case. When you state something, you have to be very careful and very precise. Precision means accuracy. You are stating exactly what you want to state. The second advantage of mathematics is that it is logical. By logical, I mean that there are certain laws or rules that follow from one argument to another. You will see as you study the course, or as in the course of this discussion, that when you present a definition, for example, mathematics will give you certain definition, and you will see that one concept naturally will lead to another concept. Mathematics is often presented in a series of statements. It is a language, and we shall get to that. And the advantage of the language of mathematics is that when you present a statement, and then from this one statement you go to the next statement, the relationship between the two is very logical. You will often find that when we have a discussion, say you have a very animated discussion about the current political situation, or say the current economic situation. For instance, right now a big concern is rising prices, and say, well, rising prices because of factor X, because of factor Y. Now you say this, but if someone asks you, do you mean factor X when other factors are not important? Do you mean only factor X? Then you will say, no, I mean other factors are important, maybe factor X is more important. But mathematician will state very clearly, if other factors stay the same, then provided X increases, then prices will increase or not. This is a statement, it's a language that is used in mathematics, in logic, and in many other places which are derived from mathematics, and this is a language which has been adopted in economics. The third advantage of mathematics, and this is very obvious and follows from the first one, is that mathematics is deductive. Now if you have read detective stories, you will know that as detective, as the word detect says, he not only detects but he also deduces. He looks for certain clues. Supposing there is a, in stories, supposing there is a murder and people in the house or somewhere the detective suspects one of them is a murder, then he or she works on 2 or 3 methods. One is, here the detective will observe what is there at the scene of the crime. Then the detective might look for the motive of the crime. Third, the detective on the basis of observation will narrow it down from all the observation, pick out the important clues. Maybe mark of shoes or whatever. You have read many stories of that kind, I'm sure. And plus, there is also the process of elimination. Supposing the detective initially begins by saying that everyone could be a suspect, everyone in the household, it looks like an inside job, everyone could be a suspect. Then one by one, the detective eliminates. No, this person doesn't have has an alibi, does not have a motive. Then person B is eliminated. This narrows it down. Now it's left with 2 people. Then maybe there's a clinching argument that helps the detective to pinpoint the actual perpetrator of the crime. This is precisely the way that mathematics proceeds. Now let me pause here for a moment to tell you that there is a slight difference, but also a relationship between mathematics and statistics. What mathematics does, and we shall elaborate on this as we go along, is that mathematics presents you with a series of deductive arguments, which means that you begin with certain assumptions, begin with certain certain axioms, begin with certain concepts, you define them in certain ways, and then you come to a conclusion. Which means economics, as I have said earlier, consists of a series of deductive statements of the type which says that if P, then Q. Now what happens with many non-economists or people who are not used to the mathematical mode of thinking is, they will say, well, in economics you are always making the strong assumptions. If this thing happens, or you are talking of a change in prices, if the price of a commodity, you have seen the demand law, you have read it in your elementary courses. If the prices of a good goes up, the demand for the good goes down. But the importance of mathematics here is to say other factors remaining constant, which means supposing today the price of a good goes up by a little amount, but suddenly you win a lottery and you suddenly come by a huge amount of money, then it is possible that even if the price goes up, you will still buy more of that good or demand more of that good simply because your purchasing power has increased even though the price has gone up. Therefore, the economist or the person using a mathematical language is careful enough to mention that the price of a commodity going up will lead to a falling demand if and only if other prices of other goods or the income or the tastes and all remain the same. Now, for instance, to continue with the demand analogy, just to end it, supposing the price of a cassette goes down, now you might be tempted to buy more of it, more cassette, but the point is that if the taste in that cassette goes and you have a taste suddenly for MP3 format of music or an audio CD format music, you may not even want to buy an audio cassette of the music. Now here, even though the price has gone down, you are not buying more of it because the taste factor is intruded. So therefore, to make a very careful statement and to make it possible to generalize it to a level of a law, it is important to make certain assumptions. We shall see how tools are used or not used. Now, when we use, I was talking about use of mathematics and its relationship to statistics and how mathematics and statistics are related. I'll just use it as a digression and we'll come back to a main discussion on mathematics itself. Now, statistics is where you have a law from mathematics, you have divides it as a purely logical series of logical statements based upon on certain concepts which you should be careful enough to define. Then you have to state a law, or you have to state the relationship among various concepts or various ingredients of the structure of your theory. Now from that you come to a conclusion. The work of statistics is somewhat different. The statistics works in two ways. Statistics works on a principle of what is called induction, which means statistics either tests your theory. Supposing you say the law of demand. Now what statistics does is it takes actual data of say prices and looks at actual consumption pattern of people, and then tries to test this hypothesis of whether the rising prices will lead to a falling demand or not. So therefore the statistics is used to empirically test what the mathematics will provide as a law. The second advantage of statistics, or second use of statistics, is to take many instances of individual cases. You take one market and see if in this market, just observation, you observe if price goes up, does demand come down? You say okay, yes. You do another study, you say the same thing, yes. You do the third study. When you do that, then you generalize, and you, by this process of induction, step by step, then you, from the particular to the general, you come to this way. But mind you, this is not a logical way of argument. This is a way of arguing from a series of observations without any prior, what is called a priori theory behind it. So you come to this sort of theorizing as well. But that is the root of statistics. Now let us get back to mathematics. Mathematics, what it does is, it gives you a series of logical statements. For instance, if you say, I'll give you simple two simple laws of logic. Supposing I say what is called the law of syllogism. If I say that all crows are black, and then you look at a bird and say it is a crow, and then you say therefore it is black, is that valid? It may or may not be. The point is, you have to say all crows are black, this is a crow, therefore it has to be black. Now this is a purely logical statement without even looking at a crow. Supposing someone tells you that outside this room there is a crow sitting, and you come up with a prior assumption that all crows are black, then from that logical statement will follow that this crow is black. It may not be empirically true. It may not be empirically true. Supposing it is falsified, and much is made of this concept of falsification, this means that your initial premise was wrong. So even if you come across a single instance where this is not true, then you have to change your assumption. I'll give you the example, another example which is given, which says that you have studied the concept of sets, and we shall discuss if a set, and you know a part of that set which is called a subset of that set, which means supposing B is a subset of A, then it means that all elements that are elements of B that belong to B necessarily belong to A. So one of the laws about this thing is that if a thing is, if A implies B, then the not A does not necessarily imply not B, but not B implies not A. Here not A and not B means the opposite or the different from A. I'll give you a simple example. Supposing I say that all cats are mammals, right? This is an assumption, this is an observation, you can proceed with this thing. My first statement is all cats are mammals. So does cat imply mammal? No, it's the other way around. A cat implies that it is a mammal. So if will I be correct in saying that if it is not a cat, then it is not a mammal? No, I shall not be correct in saying that, because if I say if something is not a cat, it can well be say a dog or a tiger, which is still a mammal. But if cat implies mammal, that is cat is A and mammal is B, if all cats are mammals, then all non-cats are not necessarily non-mammals. I just said that. But the converse is true, which means if something is not a mammal, then it cannot certainly be a cat. So you see, you are equipped with certain rules of argumentation, you are equipped with certain ways of deducing certain things which are there already before you. So once you are familiar with a mathematical concept, what it enables you to do is to have ingredients of a successful structure of argumentation and put your views correctly in terms of either explaining or exposition or argumentation. Secondly, mathematics gives you, as I said, I'm harping on this fact again and again, that it's precise, it's logical, it's deductive, but it's also very concise, which means that what you would otherwise take a lot of words to say can be reduced in mathematics, and more so as you go in more and more advanced forms of mathematics. It can be reduced by using certain mathematical symbols and explaining the relationship between them. Then you use a lesser form of space, or less words or less notations, and so on and so forth. Now, one of the things I've just explained about mathematics, now I will briefly discuss the structure of the course, that the revised course is coming to you, and then we shall go on back to our discussion about mathematics in general. Once I discuss the topics in this course, then you will probably have an idea of what mathematics is and what it can be used for in economic analysis, which is the title of our discussion today. And as we discuss the topics, I can let us discuss each topic in mathematics and give a counterpart of an economic concept where that mathematics is used to enhance our understanding of that economic concept. Now, if you were to see, the first block that we have in this course is titled Elementary Algebra. Now, this, as you can see in the slide, it is shown, it says that elementary algebra has 3 units. Now, I'll just come to each of these. The first unit is on sets, relations and functions. Sets, as you know, are nothing but simple, well-defined collection of objects. Now, once you have a concept of a set, mind you, then you are equipped with the most basic concept that can be manipulated, that can be, you can have the relationship between two sets. You can have one set which is contained in another set, which is what we discussed a little earlier, called a subset. You can have the relationship among various sets. Then you can have concepts. You can say which sets, supposing you have an organized, say an economy, you have a set of all consumers, and if you have a set of all producers. Now I ask you, is there any element that is common between the two? If you scratch your head and say, well, I don't know, well, the answer could be, supposing you talk of a self-employed or a self-working farmer. The farmer produces some goods, sells part of his good, but also consumes something from his own product and also product from others. So everybody can be a producer and consumer, and some farmers can be both. So you can have what is called an intersecting set. Now, supposing you have producers in America and producers in India, there may be nothing common, so they may be disjoint sets. What I am trying to get at is that if you conceptualize something in your mind, when you talk of any economic concept, even English concepts, certain pictures, certain associations are formed in your mind, and mathematics, the concepts of sets, gives you a way to model those and conceptualize in a logical way those various ideas that you have would otherwise be vague and amorphous. Now, sets are very important. Once you reduce them to a diagram called Venn diagram, you can immediately point out the relationship between the sets, and that will give you an idea of how to talk about the relationship among the various elements of one set or of one set and another set. Now, in the same unit, we will discuss relations and functions, which are nothing but manipulation of sets, taking elements of one set and another and seeing the relationship between them. We take what is called an ordered pair, that is a collection of pairs from each from one set, and a collection of all ordered pairs is called a Cartesian product. As you know the set, you have done it in EC5. What I am trying to say is that relations, you take set. The interesting thing is, once you understand the concept of a set, you use the concept of a set to build the concept of a relation, which, as the name suggests, talks about relationship among various elements of one set or with one set and other sets. And you have a particular kind of relation which are called functions. And the next unit will give you a graphical way to it will join geometry and algebra. It's sometimes called algebraic geometry, sometimes called coordinate geometry. It gives you an idea of putting things. You have seen pictures, you see graphs of say prices increasing or profits increasing. That is what is called coordinate geometry. That is, you have a series of axes and certain things are drawn. Then you know certain things can be expressed as equations. Now those equations can be depicted graphically. The distance between 2 points can be computed. So these are very interesting concepts, which are the building block again of first yes, if the of going ahead with certain concepts. If you want to write this point or any time, kindly ask questions, because that will make it more discussion, and I'm presuming that you are there listening to it. So please do not hesitate to ask questions and suggest something or steer the discussion in any direction that you want to, but let's make it a very animated and live discussion, and I would really appreciate that you ask as many questions and as soon as possible as we go along. The third unit is on what is called systems of linear equation. Linear means in coordinate geometry you would have studied in EEC 5 and also in the new course that we will be giving. It's depiction of situations or relationship between two variables which vary in such a way that the relationship between them can be depicted as a straight line. Now that is relationship between one variable and another variable. When you have a series of such variables, then what is called a system of linear equations, a simultaneous linear equation system is provided. Now these things are discussed in the first block on elementary algebra. Now why linear algebra is important? Why is linear equations important? Because it begins with the simplest thing that is possible. So you will notice there is a logical progress not only of mathematics per se, but even on the topics of mathematics as is presented, because you build from the simplest of concepts and go over to the more complex concepts or concepts that build upon earlier concepts. So you have a concept of a set, you have a concept of a relation, you have a concept of a function. You should know what is a variable, what is a constant, what is a parameter. Once you have that, it's like learning a language. You first learn the letters of the alphabet of that language, you learn A, B, C, D, then you learn about certain words, then you learn about certain rules of words association. You learn that at the end of every sentence you have to put a full stop, you know where to put commas, how to build a sentence. You can combine sentences to build paragraphs, you can build paragraphs to build bigger pieces of writing. Now that's the way it proceeds. Similarly in mathematics, in terms of exposition, we have tried to explain in this course, we give simpler concepts that help you to go over to more complex concepts, and these in turn help you to come yet more another concept. Before I go on to the rest of the blocks, let me pause here and tell you discuss a very important thing that is related to the use of mathematics and economics, and that is the concept of modeling or building a model. Although at this stage of BDP you are not expected to build models of your own, you will be expected to look at certain things which are actually models of actuality. What is a model? A model is a simplified assumption of reality where you pick out the most important or the most salient features of a situation and then say that, well, I assume these things, these are the relationships, and see what conclusion it leads you to. Are you familiar with certain models? Of course you are. You have done your course EEC 11. Those of you who have done course EEC 11 in BDP electives, or the basic concepts of micro and macro, when you have studied indifference curve analysis, isn't indifference curve a model of a simplified way of how consumers derive utility from the consumption of two goods or a bundle of two goods at a time? If you look at the macro aspect, look at the, if you take the economy, you know macroeconomics means the economy wide, the wider scale, big scale study of the economy. That is so complex, that is very difficult. What do? You simplify the millions of transactions taking place in the economy into four markets. You talk of the labor market, you talk of the financial market, you talk of the goods market, and you talk of the money market. And then what do? You have a concept called an equilibrium. Now mind you, you are using this every day in your other economics courses, but you forget that these are concepts which are borrowed from mathematics. Mathematics gives you both a set of concepts as well as a set of argumentative tools which you can manipulate these concepts to come to certain conclusions or give certain views. To continue with the ISLM, what is ISLM? ISLM, as you have studied, is nothing but the study of simultaneous equilibrium arising in the goods market as well as in the financial and money markets. Now, if you look at the economy as a whole, can you study the goods market separately? If you were to describe the economy, it will take reams and reams of paper, and you would not be able to do even a mediocre job of explaining the economy. So what do? You take out the you simplify the concept. You simplify the concept, hoping to capture the essential features, hoping to capture the salient features. You make certain assumptions. You come to for instance, in the indifference curve analysis, you talk in the ISLM analysis, to come back to that, you would say that there is an inverse relationship between the interest rate and the investment. You know, there is a positive relationship between saving and interest rate. So you derive an IS curve which tells you the equilibrium in the money in the goods market. Similarly, you talk of the relationship between interest rates and the money demand, interest rate and money supply. So between interest rate and income, you are using saving, investment, money demand and money supply to look at the entire concept of an equilibrium interest rate and the equilibrium level of income. So this is a model. A model is nothing but a simplified description of reality. You take out certain assumptions. Many people say, they look at the model and say, oh, this is such a simplified thing. It doesn't discuss the real world is so complex. How can you capture? That is precisely the point. Because the real world is complex, you have to simplify. If you don't simplify, then you have no hope in trying to understand reality in its entire complexity. If you take a map of a place, that map of a place only, if you take a map of India, even if you take the physical map of India, it's a very small and a very crumpled. If number one, the map of India cannot exactly be as big as India itself, therefore because the map will then be useless or impossible to make. Number two, it tells you the salient features of India. Number three, the model tells you a rough distance between, say, two cities. So there are certain purposes of which the model is used. Or if you take the model that architects make of a township that is architect is supposed to make, or a big building that the architect is supposed to make, the architect makes a miniature version of that. That is another kind of model. So model can be a simplified thing, model can be an idealized thing. So when you'll see, when many people who do not use the mathematical mode of argument will come up with statements like, well, reality is so complex, how can you be so sure of capturing reality? That is precisely the one. Because reality is so concept, you have to tweak out the essential elements, as I am saying. Secondly, you should not assume, as many people do, that mathematics means numbers only. Mathematics means talking about only numbers, talking about arithmetic. Many people, when they talk of mathematics, talk of arithmetic, and they say, well, their life is so qualitative that, you know, there are certain things which cannot be reduced to numbers, which cannot be quantifiable, and therefore they assume what cannot be quantified or what cannot be put in actual numbers is therefore useless. It is not so. Mathematics is about relationship among concepts. Now, as we shall see. Now, if we look at the next block in the course is titled Elementary Linear Algebra, and this builds on from the third unit of the first block, which was, if you remember, on simultaneous linear equation systems, and this uses the techniques of matrices and determinants in the first unit of this block. And in the second unit, it discusses linear economic models. Again, linear means relationships can be expressed by straight lines, which in economics would probably mean something like, to use your language, fixed coefficient productions. So you have known a thing called input-output analysis from your study of National Account System EEC 10. You know input-output analysis from EEC 11, and you know linear production methods from your EEC 11. The thing is, you were approaching these topics from the concept of input-output. You are approaching these things from the concept of production. But here you are doing mathematics, what a student of mathematics would do. And the interesting thing is to see two things simultaneously in this course. One is, you talk of an series of economic concepts, and then see which mathematical concept in language is an exact translation of this economic concept. For instance, I'll come to this later, but one of the things in your course, a very common word in economics is marginal. You know marginal utility, you know marginal cost, you know marginal product. Now you are wondering what is marginal? Marginal is addition of one more unit, other things remaining the same. That is a verbal way of putting it. But when you will do calculus, which is there in a block 3, and I'll come to that, when you come to a unit called partial differentiation, which you have already done, those of you who are students of EEC 5 know the concept of partial derivative. So you know what the relationship between partial derivatives in mathematics and the concept of marginal analysis in economics. In fact, marginal analysis is such an important branch of economics, a way of arguing that a whole school of thought from the late 19th century or the third quarter of the 19th century came to be called the marginalist school, and their theories collectively came to be called the marginalist revolution. And what was the revolution? The revolution was nothing but the fact that they were using the techniques of differential calculus, which had never been used in social science before that time. It had been invented, by the way, by, among other people, Isaac Newton, to study gravitation and the laws of motions of planets and other heavenly bodies. But it was being used by social scientists now in economics to study your economic process, and that the concept of marginal analysis developed. Similarly, I just said, you just saw there are matrices and determinants, there are linear economic models, and one of the interesting things, one of the examples of a linear economic model, which is not in your course of course, but I am saying this as an aside, is the concept analysis of Marxian economic analysis. And one of the criticisms that is made of a mistake, series of mistakes that Marx is supposed to have made in this analysis, in his analysis, was because of a theorem which is there in your course EEC 5, which is called the Perron-Frobenius theorem. Marx didn't know that, for the simple reason that Perron and Frobenius had not come forward with that theorem in mathematics, but later theorists of Marxian economics, theorists mind you, not activists, used that Perron-Frobenius theorem to put forward certain propositions of Marxian economic theory. So you will find, as I was saying, that the course on mathematical economics or mathematical economics in general will do two things. One, it will give you first some economic concepts and help to translate that into mathematics, and therefore showing that this economic concept is similar or better explained or more concisely explained by that concept in mathematics. But the course also takes the opposite point of view. It assumes, supposing you have done some mathematics, say till your school, certain class you have done mathematics, and supposing you stop that, you begin the process through the mathematics route or mathematics end of the story. You said this is the concept of mathematics, let's say matrix algebra, let's say set theory. Can I use set theory in economics? And say, well, this is where set theory can be used. Set theory can be used in physics or in other branches, but what is the use of set theory in economics? You as a student of this course can say, well, you know set theory, apply it here. This is what set theory can be used for to explain concepts in economics. Similarly, you know matrix algebra. What does matrix algebra have to do with economics? You say, well, this so many important concepts. I will not use the word matrix algebra first. Let us say the relationship between coal and iron and so many industries which are producing goods, but which are using the goods of other industries as its own inputs. For instance, a coal industry, when the mines in the trolleys are sent inside the mines, they are made of steel. So this coal industry is using inputs from the steel industry, but the steel industry can use certain things, inputs from the coal industry. These are inter-industry analysis, you know that. How can analysis? A very interesting topic. You can talk about it verbally, but to make it very conceptually clear, what can you do? You can invoke the use of input-output economics. And what is input-output economics? Nothing but an application of linear algebra, the theory of matrices, which you would otherwise just study as algebraic manipulations of certain concepts, certain elements that you use in input. So it makes it very live. The third block, as we say, and I will quickly go over the blocks now, is on calculus. As I was saying, the main concept is, I talked a little bit about partial differentiation earlier. There is the general concept of differentiation, which is to see, very interesting thing about differentiation is to see when I say that y depends on x or y depends on x, w, z, then you say if I change w, what will happen to y? Supposing y depends only on x, say y is a function of x. Okay, lay person would say y depends on x. You as a student of mathematical economics will say y is a function of x. Having said that, that is good enough. Now you come to the next step. Supposing x changes, what happens to y? I say agriculture is a production of land. I can also say labor, but let's say agriculture is production of land. Now I say if a land increases, will the agricultural product go up? You formulate a relationship. Now that is one thing. Now supposing I say agricultural output is a function of not only land, labor, tractors, harvester, threshers, and other seeds and other fertilizers and all other inputs. Then you will say I want to study two things. Supposing I increase all factors of production by the same amount, I want to see by how much the agricultural production increase. That will be a concept of total differentiation. If you say I want to study how agricultural product will increase or decrease or change, if I only increase the amount of number of laborers in the farm by keeping everything else the same, supposing I keep the amount of fertilizers, use the seed, use the pesticide, use the tractors, number of tractors same, I just bring in more people at the time of harvesting to cut the output or plant the seeds, will agricultural production increase? That you can talk about in general terms, but in mathematical terms that's the use of partial differentiation. Now it is a question of change. If I don't use change, if I want to do the other side, instead of differentiating, if I want to integrate or sum up over a certain range, I use the technique of integration or integral calculus. Similarly, in economics you always want to maximize profits, so you want to maximize utility. If you are rational, you want to do the best that you can, then you use the techniques of optimization, and the next several blocks are on various parts of optimization. You can see there is a unit on optimization. See, now you are going step by step conceptually, which builds from simple to the concept. You begin with the one variable case, then you begin with the optimization of functions of more than one variables. I talked about the agricultural production function. You want to maximize agricultural production. You cannot take the one variable case. You have to take many variable cases. But supposing you are just consuming one good and you want to see utility as a function of that good itself, you want to see how you can maximize or optimize the utility, then you use that case. Now you take a look at the next block. The next block talks of constraint optimization. Constraint optimization means you want to maximize something, but there are certain constraints, there are certain limitations. You are a consumer, you want to maximize your utility, but you are constrained by your budget. You are a producer, you want to maximize your profits, but you are constrained by your costs. Your costs are there, you want to maximize the profits subject to the cost constraint. It's easy to say this, but is there a mathematical tool which would help us to study this better or express this better? Yes, the technique of constraint maximization, and there is a related unit on comparative statics which deals with this only. Now we come to the next block, discusses dynamics. In sciences, that is a word derived from the sciences. If you take a look at the next slide, you will see that dynamics has this block has 3 units. In physics or in other sciences, the dynamics means a change in position. A static means something that is at a place, at a certain fixed place, and dynamics means how the particular good or object changes its position. In economics, on the other hand, dynamics means over a period of time. Say for instance, if you put some money in a bank, and you do this kind of calculation every day, you see, supposing, like there are examples, people are saying if you are at the age of 25 and you invest a certain amount of money recurringly over a period of time, then in a pension fund, in a private pension fund, then at your retirement at say 60 years, you will end up with this corpus of money. If you were to delay beginning your investment, if you were to begin your investment at the age of 35, you will get so much less. Or you just see, if you put it in a time deposit, how much you will get in a period of time. So this is a question of where time comes in. This is a question where when you talk of sustainable development, which is very important today, you talk of long run growth. You want to optimize growth, as we were talking of optimization in the previous block. You want to maximize a growth. See, India is growing and we all want to grow as fast as possible. China is growing as fast as possible. But will it have an adverse impact on environment, if not for this generation, for the successive generation? Are we depleting the resources? Now once these concepts are asked or these questions are raised, you go into the realm of dynamics, and to study dynamics you bring in certain concepts of mathematics. One is integral calculus, but as I had said earlier, integral calculus can be used for summation in general sense over a limiting thing, but it can also be used to see definite integrals. You know what definite integrals are. These are used to study the processes of economic processes over time. Supposing you are a wine maker, you want to brew wine and of a certain vintage. How long should you keep? You own a certain forest, you want to cut timber, which is not always a very good thing now, but supposing you want to stagger a certain production, a certain output and investment process, what should you do? Now all these are discussed in this block, and there are two next units. Once if you have discrete time packages, they use difference equations, what is called, and if you have continuous thing, then you use differential equations. You might say that time can go continuously, time can go discretely, that is up to us how we differentiate between time, but mathematics gives you different tools to analyze these different problems. Now to continue with this process of optimization which you did earlier, we did on constraint optimization, we had done constraint optimization. Now there is another block which is called programming, which is using techniques which are not always from differential calculus. The first unit in this is called linear programming, which means both the objective function as well as the constraints are linear. Linear means straight lines. Then there is an extension of this called non-linear programming, which is using calculus techniques, but the constraints are inequality constraints. The interesting thing about this is, for instance, supposing you say that you want to maximize utility subject to a budget constraint. Normally you would, in a simplified way, you will say where your expenditure on the goods should equal your income. But non-linear programming can deal with situations where you can say your expenditure on all goods should be less than or equal to your income. You need not exhaust your income. You can save part of your income. So that you are saying this verbally, but the interesting thing about mathematics is it throws up new techniques called non-linear programming, and the last one is dynamic optimization, which means optimization of processes over time. The interesting thing about the word programming here is that these techniques in economics or mathematics, were developed at the same time in the 1950s when computer programming was developed. So to make it sound very attractive and to draw more people to this, the suffix programming was given, although it has got nothing to do with computer programming. And the last block of this course deals with situations where people interact. It is built from matrix algebra initially, but now it has extended and it's called game theory, which talks of interacting agents. Again, it's replete with applications in sociology, political science, economics, although in India mostly economists have used this. You can study anything from voting to relationship between spouses to management and labor, union negotiations, bargaining, auctions, selling of spectrum rights for internet, whatever, using game theory. It has two units, one which discuss where situations where decisions are made simultaneously, which is called static game theory, and one where decisions are made sequentially, for instance in a game of chess, and other business applications or political applications called dynamic games. And there are equilibrium concepts presented, and there are certain mathematical tools which drop on earlier, which are sent to explain to you. So the bird's eye view of the structure of the course also is a mirror of the different concepts that we thought are important from mathematics and which can be used and which have been used, with full of examples about how you can use them in economics. On the other hand, and as an addition to this, as I said earlier, you can take some concept from economics from anywhere, from micro, macro, international trade, public finance, and then say, can I apply this mathematical tool to explain this concept of economics? And the interesting thing about economics, I'll say this before I end, of mathematics is you'll find that whether it is microeconomics, whether it's say in microeconomics, whether it's a theory of the consumer, whether it's a theory of the producer, whether it's a theory of the perfect competition or whatever, whenever you say somebody maximizes something, whether it's profits or utility, whatever, there is a common core of optimization theory provided by mathematics which you can use in different applications. So that is the use of mathematics, to make make it, to throw up patterns, to give it concision, to give it precision. So I'll end here. I'm fairly disappointed that you didn't ask any questions if you were listening to this or watching this. Thank you very much for listening this, and you can write into us at Maidangadi, IGNOU, Delhi if you have any suggestions or any questions or any queries. Thank you for watching this session of teleconferencing.